Okay, so today we begin with actual Calc 2 integration techniques. We're going to start with integration by parts. I'm not going to motivate integration by parts. It's just a little algorithm that we're going to do. Today, we're going to practice the algorithm. This is the way I was taught, and I liked it. I think it makes sense. We're going to practice the algorithm, learn how to use it, and then tomorrow I'm going to show you where it came from. In fact, I'm going to kind of show you. You guys are going to kind of show me too, though. I'll get you started, and I'll help you along if you need me to. Last time when I did it with them, they didn't need me very much. Let's see if you guys do tomorrow. Okay, so how's the algorithm work? Because there's not a lot you could do with that first problem u substitution-wise, right? Like it's x times e to the x. So u is e to the x, but then du would be e to the x. I don't see two e to the x's. You could make u x e to the x, but then you'd have to do like a product rule, and you'd have even more stuff, and I don't see very much stuff. You guys know what I'm saying? So actually, the secret to integration by parts has to do with the product rule. But here's how you do it. It's another kind of substitution, basically. So we call it a u dv substitution. It has two parts. You select a u, you select a dv. This other problem's a totally different one. Maybe I better erase it for now. Get it out of the way. So, just like a u substitution, you're trying to change an integral you can't do into an integral you can do, or more than one integral you can do. This one, you're substituting two things, kind of, though. So, the secret to this is picking a u, and then you're going to take its derivative. It's easy enough. If this is dv, what do you think I'm putting here? V. So how do you get from dv to v? You integrate. So there's like an integral built into this process, and it's right there. So I think one of the guiding statements, there's more than one, I mean you just need experience, but one of the ways I pick a u dv substitution is you have to put something right here which you can already integrate. If you put something right here you still don't know how to integrate, you're not going to make much progress, you know what I mean? So you've got to stick something right here you can integrate. There's two obvious pieces here. In this problem, you can kind of integrate either one, right? We know how to integrate x. We also know how to integrate e to the x. So that's only part of the ball game. The other one I like to refer to is you want to try to pick a u that dies. You want to pick a u that after you take its derivative once, or maybe you have to do it a couple times, it's going to die off. So those are my two rules of thumb for picking a substitution. Otherwise, you guys just need experience and it becomes easy. Pick something you can integrate here. Pick something that you can kill off here. Not because, you know, we're the only turtle in the nest and there's only a little bit of food and you have to kill off all those other turtles, but because we want to eventually kill off the integral we can't do and turn it into one we can. Okay? Terrible analogy, I'm sorry.
Why turtles?
So, which one of these things is going to die? Because we can integrate them both, but which one of these things is going to die off if we start taking its derivative? Only one of them. X. E to the x, if you take its derivative, it's just going to keep being e to the x every time, no matter how many times. So let's try that. This is x. This will make e to the x. So the integral of e to the x, it's the nicest function out there, right, is e to the x. The derivative of x is 1. Careful. Dx. So really, part of my substitution, I'm missing some notation. Can you guys help me fix the notation? We fixed that part. What's missing over here? Ah, I like that. You don't need to use your plus c in here. That's very good. Something else is missing. When you substitute, shouldn't everything go in here? Where's the dx in black? It should be right here. And that's where you integrate. And I like what you guys said about plus c. You don't have to worry about the plus c here, though, but great comment. Very good. Okay, so now, once you've selected your integration by parts, you say that this is going to be equal to, which I'll explain tomorrow, uv minus the integral of v du. This already might starting to click a little bit, but we're going to figure it all out tomorrow. For now, just remember, that's what you need to memorize. uv minus the integral of v du definitely needs to be memorized. Okay, so now you just stick in your stuff and see what happens. If you pick the right substitution, stuff will happen. If you didn't, go try another one. So uv x e to the x minus the integral. And by the way, if these were numbers, if this was a definite integral, we'll do one like that next. You just stick those here and here. But v was what? E to the x? And du is just dx, right? Did we turn an integral we couldn't do into one we could do? Yes, clearly. So this answer is going to be x e to the x, and the integral of another e to the x is again e to the x. What am I missing? Plus c. That's how you use integration by parts. Again, I still haven't motivated where it came from, but it's not like a really strange place. We'll see that tomorrow. First, I just want you picking up. All right, let's do arc sine is what I had next, right? Arc sine of x. Example number 2, the integral of arc sine of x. Whether you want to write it inverse sine or arc sine. So this is a problem that's not in the front of your book, right? I don't think it ever was in the front of your book. We never learned how to integrate arc sine. We learned how to integrate 1 over the square root of x squared minus 1, but we didn't learn how to integrate arc sine.
Participating in the Friends of Rachel groups up at the elementary need to come sign out at the Student Services Office. And teachers, this is at your discretion to let them go. Thank you.
I would not miss statistics today. Your choice, but not a wise decision probably. Okay, so I'll talk more about that in a second. U dv. What do you guys think? What should we pick? There's not a lot of. There's only really one thing. U should be dx. So then I should put that there. But if I put that there, I still can't integrate it. I'm trying to do the problem that I started trying to do.
Switch them.
Yeah. Okay, so the integral here is what? X. Good. Do we know how to take the derivative of arc sine? Yeah, we know how to take the derivative of everything. What is it? Is it 1 minus x squared or x squared minus 1? The way I remember it is the secant has an x on both sides of this. That's how I always remember. But it has x squared right next to x on the outside. So anyway, there we go. So this is equal to uv, u, v. I put it there instead because that's nicer. Minus the integral of v du. And that's something we can do. How?
Making u 1 minus x squared to u sub.
Yeah, it's just a u sub, right? I wanted to do this one with some limits of integration, so let me put those in here. I'll put them in green. Let's say they wanted to do this from 0 to 1. That means this needs to be 0 to 1. And this also needs to be evaluated with the fundamental theorem from 0 to 1. Okay? So that's something you got to be careful about. You guys already told me how to do this integral, so let's do it. Well, let's do this part first. So that's going to be 1 inverse sine of 1. We'll figure that out in a second. Minus 0 kil, right? Minus this integral, which you guys said is a u sub, so 1 minus x squared, du is negative 2x dx. So that's going to be minus the integral from 0 to 1 of du over negative 2 square root of u. I really shouldn't put these, right? So it's going to be minus minus is plus 1/2 times the integral of u to the negative 1/2 u, which is plus 1/2 times 2u to the 1/2, right? So that cancels out, that's nice. This is really just plus root u, and u is 1 minus x squared. And we wanted to go from 0 to 1. So coming way over here, it's going to be equal to, so far we've got the inverse sine of 1 minus nothing plus or minus, we got to be careful here. So I had a minus, and that minus became this plus. So it is plus, right? Plus the square root of, if we plug 1 in, we're going to get that minus, yeah, so you don't have to write that out if you don't want to, but that's going to be nothing, that's going to be 1, so we're going to have minus 1 right there. And how do you do the inverse sine of 1? Remember, you could think, what angle has a sine of 1 over 1? Oh, it's not a triangle. What is it?
It's pi over 2.
It's this spot, right? So it's pi over 2 minus 1. There we go. There's another integration by parts problem. Let's do one more. It's a little bit different. We'll call it good for today, I think. So let's see, what one did I want to do? Here's another integral we couldn't do before. Not something we could do before, right? Now maybe if the x squared was inside, we could do it, right? That'd just be a simple u substitution, but it's not inside. So, integration by parts. This is a classic, by the way. Any student who knows calculus recognizes this as integration by parts immediately. What do you guys think? What should we try? What should u be? What should be dv be? Remember, I gave you 2 guidelines.
X squared is u.
We can integrate either one of those, right? We know how to integrate sine, we know how to integrate x squared.
X squared is going to die off.
But x squared is going to die off faster. That's the way you want to go. And you won't even remember my 2 methods of advice after a while, maybe. I don't know, maybe they'll really stick because I tried to make one of them funny. After a while, you're just going to do this. It's going to be second nature. But anyway, let's see if that worked. So it's not dead yet, right? You're going to have du is 2x dx. I really should have put the dx right here. Is that what you're saying, John? Yeah. Yep. Integrate sine and you get, remember, integrate. Take the derivative, you get cosine. So integrate and you get negative cosine. Okay, so this is equal to uv. So x squared negative cosine of x. See, I fixed it up right there as I was writing. Minus the integral of v. There's another minus, so I'm just going to say plus. What else do I need? V du. So I still need this 2x dx. And if I'm thinking, you know, I'm going to go like this. It's cosine times x dx 2. We don't have any limits of integration to worry about, so we're good to go. That integral. How do you do that one? That's right. Kyle said integration by parts because something's still not dead. What's still not dead? That guy. So, second integration by parts. This is an example of repeated integration by parts. Sometimes you have to use it 5 times. We're going to have a way to avoid that though. So let's say m equals x. So that's what we wanted to kill. dn equals cosine. Derivative of x is 1. The integral of cosine is sine, yep. I should put a dx here. So now I'm going to have, try to color code it for your convenience, your viewing pleasure. See my bracket? Watch out for that. Now we're going to have UV. So what's UV in this red stuff? X sine x, or mn, right? Mn minus the integral of, for UV it was UV minus integral v du, so mn minus integral of n dm. That's an integral. It's very simple. So our integration by parts has been successful. We can say our answer is going to be negative x squared cosine x plus 2x sine x watch that, minus 2 what? Integral of sine, derivative of sine is cosine. I do it every time, so derivative of sine is cosine, that's my guide. So the integral of sine is going to be negative cosine. There we go. Repeated integration by parts. Next time we'll look at where this algorithm came from, and we'll do some more problems that might be a little more involved, especially the wraparound problem. See you next time.